Right, the first problem of this revision sheet, have you been able to solve this problem? Yes. All of you? Is there anyone who wants me to solve this problem? First problem 1? I'll just solve it and you'll see if you've done it right or not. Right? So waves revision sheet 1, problem 1. We have the case of a uniform rope of mass m and length L. Mass m and length L hanging from an elevator ceiling. This is an elevator ceiling which is accelerating upwards with a constant acceleration a. That accelerates upwards with a constant acceleration a. We want to find the time taken by a transverse pulse to travel the whole length. That means to travel from, let's say, P to Q. Now, the velocity of transverse waves in a string is given by square root of T by m, right? T is the tension, m is the mass per unit length, right? In this case, let me call it lambda because m is the total mass, so mass per unit length, let me call it lambda, right? Now, for a situation of this kind, this string has mass, the tension would be different at different points. So let me call this position x equal to 0, this position x equal to L. Let me find out the tension at x0. Let me find out the tension at x0. Now if the tension at x is Tx, then if I draw the free body diagram of PR, then this Tx and the weight of this together will produce an acceleration A on PR, right? So which means tension at x minus the mass of this. Mass of this is lambda x into g. That's the weight acting downwards. Together they produce an acceleration A. Let's say I can call it lambda L. I can call it lambda L, right? Together they produce an acceleration A on the segment PR. So the tension at x evidently is going to be given by lambda AL plus GX. Yes or no?
So lambda into x A.
Oh, lambda into, sorry, XA. Lambda into for this length, yeah. So this gives me lambda x into A plus G. Lambda x into A plus G is the tension at x. So the velocity at r, which is like dx dt, the velocity at r which is like dx dt is going to be given by root T tension at x, which is lambda x into A plus G divided by the mass per unit length lambda, right? Lambda gets cancelled and now it's easy to integrate this. You have x power minus half dx is root A plus G dt. Integrate both sides. At time t equal to 0, x is 0. At time t equal to t, x is L. So this will give me the time t it takes to travel the whole length. I hope you had got it right all by yourself also, right? This is what you did. Problem 2. We have one end of a thin long uniform string, having linear mass density lambda is fixed to a wall and the other end with a block which can move along a vertical rail. So this is a vertical rail. This is a vertical rail and there is a block which can slide up and down along this rail, right? The other end of the string is connected to a fixed wall. The other end of the string is connected to a fixed wall. The string is horizontal and has a tension F. The string is horizontal and has a tension F. If the block starts to execute SHM with the rail with amplitude A and angular frequency omega, We want to calculate the energy transferred to the string during one complete oscillation of the block and the maximum rate of energy transferred to the string, right? That means the power associated, Okay. Say, let me draw the snapshot view. Let me draw the snapshot view of the wave at a certain instant of time, t. Say the snapshot view of the wave is this, amplitude A, etc., right? This is the snapshot view of the wave. Let me call this the y direction, let me call this the x direction. And let's say at time t equal to 0, the block starts executing SHM in 0 phase. From the mean position, the block starts, right? So the displacement characteristics at x equal to 0, the displacement characteristics at x equal to 0 at various instants of time would be y equal to, at x equal to 0, it's going to be a sine omega t, a is small a in this case, right? And like you already know, the displacement characteristics at any given x would lag in phase, and at any given x then the displacement as a function of time t is going to be a sine omega t minus x by v, right? That's y as a function of time. Okay, now at this instant time t, the block is here, which is executing SHM in the y direction. This is the position of the block, right? If F is the tension in the string, then the string exerts on the block, upon the block a force F like this is what the string exerts on the block, right? Tangentially, because the tension will always be along the tangent, and it does so at an angle theta with respect to the horizontal, right? Now what is important is the force exerted by the string on the block in the vertical direction, right? The F sine theta is important. The F sine theta is the force that the string exerts on the block in the vertical direction, right? Now, so it would be nice if I knew theta, right? Now what is theta? Theta is really the, tan theta will give me the slope of this graph at x equal to 0, right? So what I do is I look at this, I differentiate this with respect to x and then put x equal to 0, and then I put x equal to 0. So then tan theta is going to be given by dou y dou x at x equal to 0. At an instant of time t, at x equal to 0, tan theta would be dou y dou x, right? Which then is evidently minus a omega by v cos omega t minus x by v at x equal to 0, right? Put x equal to 0, so this will simply become cos omega t. So this would be minus a omega by v cos omega t. Now the string is given to be very thin. That means mass per unit length is very small. For the string, the mass per unit length is very small. Therefore, the velocity of the string, velocity of the wave, root t by m, will be very large. If m, the mass per unit length, is very small, v will be large. Yes or no? The wave velocity will be large because m is small, it's a thin string. So mass per unit length will be very small. So v is large. Now if v is large, do you realize that this denominator is large? So tan theta will be small. So tan theta will approximately be equal to sine theta, that too. Right? See, we need f sine theta. So then, tan theta at an instant of time t will approximately be equal to sine theta equal to minus a omega by v cos omega t. Okay. Now, the force exerted in the vertical direction is F sine theta. The force exerted by the string on the block in the upward direction is F sine theta. The velocity of the block is going to be obtained by differentiating this, would be a omega cos omega t at an instant of time. A omega cos omega t would be the velocity of the block. Right? Now, velocity of the block, so therefore the power associated with this force would be F sine theta into Vb. F sine theta into Vb. Right? Now this is about the force that the string exerts on the block. The block exerts on the string negative of this force, that means minus F sine theta, because we want to find the energy transferred to the string by the block. So we use a minus F sine theta into Vb, because minus F sine theta would be the force that the block exerts on the string. This F sine theta was the force that the string exerted on the block. So the block exerts on the string a force like this, right? And the velocity of the string at this point is also Vb, same Vb, right? So the power that the block transfers to the string is this. The power that the block transfers to the string is this, yes or no? Where sine theta you can replace by minus a omega by v cos omega t, right? So this I can write as F sine theta, which is a omega by v cos omega t. Vb is a omega cos omega t. Now, obviously the maximum power associated would be when cos omega t would be 1. That means a squared omega squared by v is the into f is the maximum power associated. The maximum power is this. Power is a function of time in this case, and the maximum power is this. P max transferred to the string is F a squared omega squared by v. That happens at all times when cos omega t is 1, right? Now, the power transferred to the string in one complete oscillation is going to be integral p dt. T runs from 0 to 2 pi by omega precisely. That's the total power transferred in one complete oscillation. That's the total energy transferred in one complete oscillation. In one complete oscillation, this is the energy transfer, which you can readily integrate. P is known as cos squared something, right? That is what the idea is. Are you all fine with this? So could you solve the problem yourself also? No? Okay, you solved it? Very good, very nice. Three plane sources of wave of frequency n1 equal to 400 Hertz, of n2 equal to 401 Hertz, n3 equal to 402 Hertz are sounded together, and they have an amplitude A each. A detector receives pulse from all these three sources simultaneously, and it can detect signals of amplitude greater than or equal to A. We want to calculate the period of one complete cycle of intensity, and the time taken or the time for which, it must be the time for which the detector remains idle in each cycle of intensity. Now this is simple. Let's say the point where it all occurs, superimposition is x equal to 0, right? So then the displacement by this is of the form, say A sine 800 pi t, 2 pi n, omega is 2 pi n t, plus A sine 802 pi t plus A sine 804 pi t. That's a disturbance produced at the point of observation. We can combine all of this. We can combine this and this so that we have this, right? So then this is like 2a sine c plus d by 2 cos c minus d by 2 plus a sine 802 pi t. This is like a 1 plus 2 cos 2 pi t sine 802 pi t. Yes or no? So the disturbance at the point of observation could be looked upon as simple harmonic oscillation with angular frequency, with frequency 802 pi, with n equal to 802 pi, 802 with n equal to 802 hertz, omega equal to 802 pi, right? And with a time varying amplitude. The time varying amplitude is A into this is the time varying amplitude. So if the amplitude at the point of observation varies with time, the intensity which is proportional to the square of the amplitude will also vary with time. So the time varying amplitude, which is of importance to us, is A as a function of time is A into 1 plus 2 cos 2 pi t, right? Easy to see that amplitude would be maximum when cos 2 pi t is 1. Every time cos 2 pi t is 1, the amplitude would be maximum and intensity would be maximum. So for A max, I max occurs, and this happens every time cos 2 pi t is 1. Now cos 2 pi t is 1 means 2 pi t must be 0, 2 pi, 4 pi and so on and so forth. So 2 pi t must be 0, 2 pi, 4 pi and so on and so forth. So t must be 0, 1, 2, 3. At these instance of time, you have a maximum intensity available. Now, again, do you realize that from one maximum to another, a second has elapsed. 1 second has elapsed. And in this 1 second, from t equal to 0 to t equal to 1, realize that all possible values of amplitudes and therefore all possible available intensities will appear. Therefore, in 1 second, you have the entire set of intensities, the entire set of amplitudes available. Therefore, the periodicity of intensity is 1 second. In 1 full second, all available intensities will make their presence felt. Right? So the period of intensity is 1 second. 1 second is a full cycle for the detector. In this 1 second, the detector perceives all available intensities that could be produced. Right? Now, however, the detector has its sensitivity. It detects only, see, those signals in which the amplitude is larger than capital A. Right? There would be times when the intensity would be less than A. There would be times when intensity would be, amplitude would be greater than A. So, whenever the amplitude is greater than A, the detector is able to register those intensities. But whenever the amplitude is less than A, it cannot register those intensities. So, less than A means every time cos 2 pi t is less than 0, it will become less than A, right? So, the idling period of the detector in 1 second, idling occurs whenever cos 2 pi t is less than 0 in a 1 second period, every time cos 2 pi t is less than 0, the detector will idle, right? Cos 2 pi t less than 0 means 2 pi t would either belong to the second or the third quadrant, right? That means 2 pi t less than pi greater than pi by 2, or rather greater than pi by 2 less than 3 pi by 2. This is the idling period. That means t greater than 1/4 less than 3/4, from t equal to 0 to 1. From t equal to 0 to 1, it idles in this span. That means the span is half a second. 3 by 4 minus 1 by 4, that means half a second. So it idles in half a second, and then when it goes to the third and the fourth quadrant, the fourth and the first quadrant, it becomes active. So in every cycle of intensity, it idles from 1/4 to 3/4 of a second. That means half a second. It idles for half a second, it's active for half a second. That is how it happens. I might have discussed the same problem in class 11, but reason I chose to discuss it again is because when I discussed it last time, I was not very sure that you understood everything that I said. So, I deliberately had it again. A uniform string of length L is fixed at both ends such that tension T is produced in it. The string is excited to vibrate with maximum amplitude A0. Calculate the maximum kinetic energy for the string for its fundamental tone for the first overtone. Okay. So we have in the fundamental mode, we have the string vibrating with nodes at the ends and an antinode at the middle. An antinode in the middle and nodes at the end. That's what we have, right? Now, say mu is the mass per unit length. Mu is the mass per unit length of the string. The velocity of transverse pulse in the string is root T by mu, right? The velocity of transverse pulse is going to be root T by mu. In the fundamental mode, realize that the length L will be equal to lambda by 2, right? The length will be equal to, therefore lambda will be 2L. Lambda therefore will be 2L. Lambda is 2L, and therefore the fundamental mode of vibration would have frequency gamma naught equal to V by lambda. That means 1 by 2L root T by mu. Right? The omega of oscillation of the constituent particles would be 2 pi times gamma naught. So 2 pi by 2L root T by mu. 2 pi by 2L root T by mu is the omega of oscillation of the constituent particles. Each of the constituent particles is executing simple harmonic motion with angular frequency omega, but with amplitude that varies with x. Now, if this is x equal to 0, this is x equal to L, then amplitude as a function of x is going to be given by the maximum amplitude, which is given to be A0. Maximum antinode means maximum amplitude A0 sine kx, where k is the wave number 2 pi by lambda. A0 is the maximum amplitude. At x equal to 0, it's 0. At x equal to 0, it's 0. So ax, A0 sine kx, right? So at a given x, if I choose a small length of the string dx, then this is like a particle executing simple harmonic motion with amplitude ax and angular frequency omega. So the total energy of this oscillator will be the maximum kinetic energy also, right? So the total energy of this oscillator is going to be half of the mass of this oscillator, which is mu into dx. Omega square a squared. Omega squared, we've known omega, so omega squared a squared. A at x squared means a naught squared sine squared kx. That's the total energy of this oscillator, right? What is k, by the way? K is known to us is 2 pi by lambda, and lambda, as you know, is 2L here. So this is 2 pi by 2 lambda, 2 pi by 2L, which means pi by L. So k you can plug in as pi by L. That's the energy for this. The total energy then would be sum of all of this, where x varies from 0 to L. That's the total energy of all oscillators from x equal to 0 to x equal to L. And it's also the maximum kinetic energy of the string. Right? And when does the maximum kinetic energy occur? When all the particles are at the mean position. At the mean position. When is the maximum potential energy? When all particles are at the amplitude position. Right? And if I've done it for the fundamental mode, I want you to be able to do it for the first overtone, where there will be two loops. Will you be able to do it in exactly the same manner? Fifth, we have a metal rod. This is a metal rod with 2 points fixed, A and B. This is 30 centimeters. This is also 30 centimeters. The total length is 100 centimeters, so this is 40 centimeters. The density of the material of the rod is given to be 9,000 kilograms per cubic meter. The Young's modulus, it's not gamma, it must be Y, is 1.44 into 10 to the power 11 Newton per meter squared. That's the elastic property of the medium. We want to be able to find the minimum and the next higher frequency of natural longitudinal oscillations of the rod. Okay. Now, the velocity of longitudinal waves in a medium is given by what? Root over? In solids, it's given by root, y by rho. Right? In fluids, it's given by root, b by rho. B is the bulk modulus. For gases, what is bulk modulus? Yes, depends on the nature of the process. It could be either the pressure or gamma times the pressure. In an adiabatic change, it's gamma times pressure. In an isothermal change, it's V. In general, it's minus V dp dv. Bulk modulus is minus V dp dv. Right? All of you understand this? So now it's a solid. The velocity of the longitudinal pulse would be root y by rho, which can be calculated. Right? The velocity of the pulse, longitudinal pulse, is going to be root y by rho. Now, let's examine what happens here. At the ends, it's bound to be an antinode because these are open end, they have greatest flexibility to move. At A and B, we have forced nodes. Now, in a very general sense, we could have had, let's say, P loops here between A and B. Between A and B, they could be P loops. Now, between this end and this end, they could be an antinode at the end, and there would be Q loops, let's say. This is Q loops, and at this end there would be again Q loops, Q full loops plus lambda by 4. Do you realize that Q loops plus lambda by 4, yes or no? At the ends again you'll have Q loops plus lambda by 4. Okay. Now between A and B, P full loops, and each loop is like lambda by 2. So what is this length equal to? P into lambda by 2. This length is P into lambda by 2, and that must be equal to 40 centimeters. Right? Now at the ends, Q full loops would mean Q into lambda by 2 plus lambda by 4. And that's 30 centimeters. P and Q are integers, positive integers, right? We want to find the smallest P and the smallest Q. That will be commensurate with this condition. Yes or no? If I divide, I have P by 2Q plus 1, 4, 2, so 2 by 3. P by 2Q plus 1 is 2 by 3, is 2 by 3, right? Can you see that? Now, the smallest P and the smallest Q. Very clearly, the smallest P must be 2, the smallest Q, 2Q plus 1 must be 3, so Q must be 1. Is it not? This is equal to 2 and this is equal to 3. So that will give me P equal to 2 and Q equal to 1. Therefore, this then would be the fundamental mode of vibration. This would be the fundamental mode of vibration. Now, once I know P or I know Q, say for example I know P in the fundamental mode, so I can plug in P equal to 2, solve for lambda. So I know the lambda in the fundamental mode, I know the velocity of the wave anyways, so V by lambda will give me the fundamental mode of vibration, will give me the fundamental mode of vibration of the string, right? You know? Now, the next higher mode, I want to find the next higher mode. Realize, no, this, if I multiply both sides, both numerator and denominator by 2, then this is not possible, because P can be 4, but 2Q plus 1 can't be 6. Can 2Q plus 1 be 6 for an integer Q? 2Q plus 1 is odd. No, it can't be 6, right? So what I do is, let me multiply both numerator and denominator by 3. Now, P can be 6 and 2Q plus 1 can be 9, right? So this gives me the next higher mode of vibration, P equal to 6 and Q equal to 4, isn't it? 2Q plus 1 equal to 9, so Q equal to 4 and P equal to 6. So then in the next higher mode, I know P equal to 6, and therefore I know the lambda for that mode of vibration. I know V by the new lambda will give me the new frequency, the next higher mode of vibration. Now, can I multiply both by 4? No, because then this will become even. 2Q plus 1 can't be even, but the next mode would be when I multiply both by 5. So that will give me the new P, the next higher P and the next higher Q. So then it's 2 into an odd number divided by 3 into an odd number. So 2 into an odd number will be P, 3 into an odd number would be 2Q plus 1. That is how it's going to be. Will give me the various modes of vibration of the rod. Clear? A plane wave propagates along positive x direction in a homogeneous medium of density rho equal to 200 kilograms per cubic meter. Resulting in oscillation of the particles of the medium, Space density of their oscillation. After all, if I'm exciting oscillations, then there is energy per unit volume in the medium because of the oscillations of the particles of the medium, SHM of the particles, right? The energy density, E, is given to be 0.16 pi squared joules per cubic meter. That's given. And the maximum shear strain is given to be 8 pi into 10 to the power minus 5. That's the maximum shear strain. And this is a wave traveling in the plus x direction. Another piece of data that's given is there are 2 points, say P, which is 1, 1, 1, and Q, which is 2, 2, 2, all in meters. The phase difference between these two particles, delta theta, the phase difference between these two particles, say delta theta, is given to be 144 degrees. Assuming at time t equal to 0, the phase of the particles at x equal to 0 be 0. That means, the oscillation of the particle at x equal to 0. At x equal to 0, the oscillation of the particle is given by a sine omega t. For the particle at x equal to 0, the oscillation is given by a sine omega t. So in general, it's a wave traveling in the plus x direction. So the wave description is going to be given by a sine omega t minus x by v. T minus x by v. Yes or no? We want to find the wave equation, and so we need omega and v. We essentially need omega v and the amplitude a, right? Is the wave longitudinal or transverse? Hey, you understand what shear strain is? Like this, that's shear strain, right? I hope all of you understand this, shear strain. Relative displacement of the particles, like this, is shear strain, which will change the shape, of the medium. That's shear strain, right? Now, in a longitudinal wave, when the wave travels in this direction, the particles move like this. That's not changing the shape of the medium. What exactly I mean by change of shape? Give me this. See, this is one face and this is one face. This is a medium. And this face is being moved up and this face is moved down. So the shape changes. Do you realize that? The shape changes. That's shearing. Shearing can lead to tearing. I will not tear this. If I do this, then that's tear. When you rip it apart, actually you are exerting a shear stress. A shear will tear, right? So you understand, so a longitudinal wave produces displacement of the particles in the same direction in which the wave is traveling, and therefore will not produce change of shape, will produce compressions and rarefactions. But if the wave is traveling in this direction and the particles are displaced relative to each other like this, therefore the medium gets sheared. We say the medium gets sheared. You know what I'm saying? The medium is getting sheared, right? The displacements of the particles are like this, and the wave disturbance, the wave motion is traveling like this, and the particles get displaced this way, causing the medium to get sheared, right? That's now. So the maximum shear strain is given to be this. Maximum shear strain would be when, let's say, at the relative displacement between two adjacent particles is the maximum, right? After all, the relative displacement of two nearby particles will be different at different times because they are executing oscillation like this. So whenever the relative displacement between two nearby particles is the maximum, then in that region we say that there is maximum shear strain. So do you understand what this shear strain is all about? Got me? Now, first of all, let's identify what this joules per cubic meter means. In a certain region, let's say, this is the x direction. Say this is the x direction, right? And say this is 1 meter length of the medium. The wave, the disturbance is traveling in this direction. So this is say one length in the direction of traversal of the wave. And there is an area like this which is 1 square meter and this is 1 square meter. So what would be the volume of this region? 1 cubic meter, right? The total energy in 1 cubic meter of all the particles executing SHM, that's 0.16 pi squared joules per cubic meter. Yes or no? Now the total mass of this region, 1 cubic meter region, would be rho into 1. That's the total mass of this region. So half of the total mass into omega squared into a squared. That's the total energy in 1 cubic meter, and that must be E. That must be 0.16 pi squared joules per cubic meter. Right? Now, P and Q, the phase difference between them would be because of the difference in x's, because the wave is traveling in the x direction, so phase difference is brought about because of the difference in paths along the x-axis. So the difference in paths along the x-axis is 1 meter, right? So the phase difference brought about for lambda is 2 pi. So for 1 meter, the phase difference would be this, 2 pi by lambda into this, where lambda is the wavelength of the wave, and that's in radians 144 into pi by 180 radians, because this 2 pi by lambda into 1 is in radians, right? So you can solve for lambda of the wave. Lambda of the wave therefore is known to us, right? Now you know the lambda of the wave. Now in this, the shear strain is actually, realize that change in y for a small change in x, that's shear strain. Dou y dou x actually, dou y dou x is the shear strain. Change in y over a small dx. If the difference in y's is dy for a small length dx, if the difference in y's between the two particles separated by dx is dy, then the shear strain is characterized by the difference in their y's, dy's, divided by the line separating them, which is dx. So dy dx measures the shear strain, at any given x, then that's going to be minus a omega by v cos omega t minus x by v. That will give me the shear strain at various times for various values of x. That's the shear strain, dy dx. Dou y dou x, to be more strict, it's dou y dou x, right? Is it not? Do you understand why this is the shear strain? Now the maximum shear strain is a omega by v. That's given in the problem. Phi naught must be a omega by v, the maximum shear strain, right? So a omega by v is h pi into 10 to the power minus 5. So we have lambda known from here, and then from this equation and this equation you can solve for a and omega. V you can write as n lambda, n is omega by 2 pi, is it not? I hope you understand this. So you can solve for a from this because you know lambda, right? V as omega by, right, n lambda, which is omega by 2 pi lambda, omega will get cancelled. So you can solve for a from this. Once you know a, you can plug in a, you can solve for omega because rest all is known to you. Once you know omega, you know a, then you know the displacement as a function of time for various values of x. And again, the nature of the wave has to be transverse, not longitudinal. Longitudinal waves will produce a pressure pulse, will not produce shearing of the medium. So if there is a medium which can't get sheared, in that medium a transverse pulse cannot travel. You know what I'm saying? If a medium resists shearing or can't get sheared, then it cannot be a home for a transverse pulse. It will only generate a longitudinal pulse, right? And if it's incompressible, then it will not produce a longitudinal wave. Because for a longitudinal wave, you need to have compression rarefaction pulses. So you need compression of the medium. If it's incompressible, you can't have a longitudinal wave, right? Three sinusoidal waves have the same period, but their amplitudes are 1/2, 1/3. And their phase angles are 0, π/2 and pi. We want to find the equation of the resulting wave obtained by the superposition of the three waves. Obviously we want to know two things about the resulting wave: amplitude and phase, and the phase, right? So let me draw the phasor diagram. 1 unit along the zero phase line. There is 1 unit along the zero phase line and half a unit along π/2. Half a unit along π/2 and then 1/3 unit along pi, right? The resultant of all these vectors will be this polygon law of vectors. This would be the resultant. This length would be the required amplitude and this angle would be the required phase, right? Okay, so this is a/3, a/2 and this is a/3 and therefore this would be 2a/3 because this whole thing is a 2a/3 and this is a/2. So obviously the required amplitude AR is going to be root a squared by 4 plus 4a squared by 9, which is 5a/6, and this angle theta is such that tan theta would be 3/4, right? And therefore the required displacement, suppose they were all sinusoidal, the required displacement characteristics produced by the net of all these would be 5a/6 sine omega t minus kx plus theta, where theta is such that tan theta is 3/4, right? This is the y versus x. Clear? Number 8. Now, a sound of intensity 27 I naught is produced at A. It travels down to the point B along this path and this path. There are three paths. And at B, no sound is heard. At B, no sound is heard. We want to find the wavelength of sound, the value of x. Assume that sound energy is equally distributed along the three paths. That means 27 I naught means 9 I naught, 9 I naught, 9 I naught. Right? Equally distributed. That means the amplitude will be proportional to square root of intensity. That means the amplitude when it arrives at B for all the three disturbances would be some 3 times a constant root I naught. 3 times a constant root I naught. A constant into 3 root I naught would be the amplitude of all the three waves arriving at B. Now, there are these three disturbances that arrive at B and produce no sound, destructive interference. They are of equal magnitudes, right? Which means for them to produce no disturbance, and at B if I draw the phasor diagram of the three, then the phasor diagram must constitute sides of an equilateral triangle taken along an sides of an equilateral triangle taken in order, because then the net would be 0. 3 No, equilateral triangle in this case because they have the same amplitude. So they are represented by the same length. Therefore equilateral triangle. Otherwise any triangle, but in this case they have the same amplitude. Therefore they are represented by same length of their phasors. Right? So disturbance 1 is like this. A units along the zero phase line, let's say. Disturbance 1 is A units along the zero phase line. Disturbance 2 would be like this, and disturbance 3 would be like this. And the three disturbances constitute sides of an equilateral triangle. Now, because it's an equilateral triangle, 2 is ahead in phase compared to 1 by an amount 2 pi by 3, right? 2 pi by 3. 2 is ahead in phase compared to 1 by 2 pi by 3. 3 is ahead in phase compared to 2 by an amount 2 pi by 3. So 3 is ahead of 1 by 4 pi by 3. 2 is ahead of 1 by 2 pi by 3. 4 pi by 3 and 2 pi by 3. Okay. Now, the phase difference between 1 and 2. The phase difference between 1 and 2, 2 minus 1 is 2 pi by 3. But look at their paths. What's the path difference? L is the diameter of the semicircle. So pi L by 2 is the length of this path and L is the length of this path. So the path difference is pi L by 2 minus L is the path difference. Now the phase difference is 2 pi by lambda is the phase difference between 1 and 2, and that must be equal to 2 pi by 3. Yes or no? Now between 1 and 3, 1 is this path, 3 is this path. Right? This length is x units, this length is also x units. But this L and this L is the same path. Therefore between 3 and 1, what's the path difference? 2x. 2x is the path difference between 3 and 1. So 2x is the path difference. So therefore phase difference is going to be 2 pi by lambda into 2x is the phase difference, and that's going to be 4 pi by 3. Right? I can solve for lambda from this because I know L. Plug in the lambda and I can solve for x. Clear? So find the equation of the three waves arriving at B. So one of the waves, let's say the zero phase, is A sine omega t. The other wave is like A sine omega t, that is 2 plus 2 pi by 3. The third one, when it arrives at B, is of the form A sine omega t plus 4 pi by 3. Problem 9. Solve this. Do you need help with 9? Anyone? No? Okay. 10. A distant double star consists, you know what a double star system is? Two stars having a common center of mass, and they move in a common circle with the same time period and in the same sense. That's a double star system. So we have a double star system comprising of dense stars of mass m, m, which emit monochromatic radiation of the same frequency. They emit waves of the same frequency. Wavelength lambda of radiation varies periodically with time period t equal to 31.4 days. If, it must be if delta lambda by lambda max is 10 to power minus 4, calculate the distance between the stars and their mass Now, first of all, we'll assume that the observer is very far away, right? Now, one star is here, the other star is here. Both emit the same frequency of radiation, right? Let's say at this instant, this star has a velocity Vs to the right, and this star to the left, and this star has a velocity Vs to the right. Right. Now the observer is stationary. Do you realize that at this point the star is receding away from the observer? So because of Doppler effect, the frequency, the wavelength here is going to be a maximum. The wavelength here is going to be a minimum. Wavelength from this will be a minimum. Wavelength from this would be a maximum, right? So in this case, lambda max and this lambda min. That is as perceived by the observer. Lambda max and lambda min as perceived by the observer. You know what I'm saying? Why? Because at this point, frequency will be minimum, so lambda will be maximum. At this point, the frequency would be maximum because of Doppler's effect, and lambda would be minimum. C is the velocity of light. So can I say that 1 by lambda max is 1 by lambda naught, C minus 0, O is the velocity of the observer, divided by C plus Vs. That's lambda max. This is from the observer to source, so minus Vs, so plus Vs. I hope you realize that, right? That's 1 by lambda max. 1 by lambda min is 1 by lambda naught, C minus 0 by C minus Vs. That's 1 by lambda min. Now, in half a revolution, right? We have lambda max and lambda min each appearing twice in half. See, what's given in the problem very clearly is, as you can read, the time period of variation of lambda is 31.4 days. That means this must be the time taken to do this must be 31.4 days. This must be 31.4 days. That means the time taken for a full revolution would be 62.8 days, right? So the time period of revolution is 62.8 days. Right? So from this, you can find omega 2 pi by t rev, and you can find the velocity of each star as omega times, let's say, a is the radius of this. Omega times a would be Vs, right? So this you know, Don't have to do the calculations, I just want you to know the concept, ditch the calculations. Now delta lambda by lambda max, that means the maximum value of this, right, is going to be delta lambda is like lambda max minus lambda min, that's the maximum difference in lambdas, divided by, this must be lambda min, so that this ratio is maximum. Yes or no? You realize what I'm saying? We want maximum ratio of this, so numerator must be maximum, delta lambda is maximum for lambda max minus lambda min, and denominator must be minimum, so that the ratio is the largest. And this is given to be 10 to power minus 4, right? You can use this lambda max minus lambda min and plug into that equation, lambda max minus lambda min from this, and you can plug into that equation, right? Now they are executing this circular motion because of each other's gravitating influence, right? That means the centripetal force that each one requires, mvs squared by r, must be because of the gravitational attraction that it, right, is going to be gm squared by 4a squared. That is the sum total of this. The rest is calculations. I don't want you to do out any calculations, right? Two thermally insulated vessels of volume V1 and V2 are filled with oxygen and connected by a small tube equipped with a valve. This is a valve here. The pressure in them initially is P1 and P2, and the temperatures are T1 and T2. M is the molar mass of oxygen. We want to find the velocity of sound in oxygen when the valve is opened and thermal equilibrium is reached. Now, so there is a thermal situation before we look at the velocity of waves. What we really need, look at what you need. In order to find the velocity of wave, you need the final common temperature. Then root gamma RT by M. Root gamma RT by M will give you the velocity of sound. Gamma you know for oxygen, M is the molar mass. T is the common temperature once they reach thermal equilibrium. Now, the whole thing is insulated, so delta Q is 0. No work done because there is no change in volume. That means for the system there is no change in internal energy. Yes or no? Now, I can find the number of moles here, N1, which is P1 V1 by RT1. I know the number of moles here, N2, which is P2 V2 by RT2. I know the number of moles in each, right? The total internal energy of this is N1 CV T1 plus N2 CV T2, right? That must be equal to N1 plus N2 CV into final common temperature. Yes or no? Initial internal energy must be final internal energy. So this will enable you, you know N1 and N2, so you can solve for T. And once you solve for T, the velocity of sound is going to be root gamma RT by M. Right, Laplace. Yes or no?